In this video, I'll discuss thermal analyses. You may be wondering, why should we run a thermal analysis? Thermal analyses provide us with temperature profiles and insight into energy transfer. This is most useful when we have parts that have a thermal failure criteria, like a computer chip, or when safety is a concern, like the radiator you see here. We want to validate that this radiator would be safe to touch while it is in operating conditions. Using probes and planes, we can obtain precise values anywhere in the model. Planes can slice into the model, allowing us to see inside the model as well as the external surfaces. Probes can be aligned to the model's external surfaces or placed internally as well. Let's walk through how to set up and run a thermal analysis. We bring our geometry into the simulation workspace. As we enter the simulation workspace, we are prompted to create a new simulation, so we'll select Thermal. At this time, we can access the study settings and modify our mesh settings if desired. Here, I'll assign the same mesh size that I used in the thermal tutorial. Adaptive meshing can also be enabled here. Adaptive meshing allows the mesh to automatically change due to the result gradients, and the solution is recalculated. This will increase the time it takes to solve the analysis. To save time while running an analysis, it is often beneficial to remove parts that are not necessary for the simulation. This is typically referred to as suppressing objects. To handle geometry changes for simulation, we do this in the Simplify workspace. In this analysis, we are interested in the temperature of the fins, so we can remove the fittings and the fluid. To remove them, I right-click on the bodies or components in the browser and select Remove. Materials can be modified if they were not assigned in the modeling workspace. We assign thermal loads to provide an energy balance. Heat in has to equal heat out. An applied temperature load will provide an infinite amount of energy to maintain the specified temperature, so it can be used as a heat sink or a heat source. In this case, the inside walls of the pipe will be at the same temperature as the water coming from the boiler/water heater. We apply a convection load on the fins where the air in the room would be removing heat from the fins. This load is calculating the amount of energy to be removed based on the reference temperature and the fin temperature. We want to be careful with the selection process not to select the area where the fins meet the pipes, as they will not be cooled by air in that area. Similarly, radiation loads calculate the energy transfer based on the reference temperature and the surface temperature of the fins. Radiation heat transfer can become the dominant form of heat transfer due to the temperatures in the radiation heat transfer equation being raised to the fourth power. This is especially true when natural convection is cooling your design. We define how the bodies contact each other. In this case, we'll use the automatic bonded contacts. Now, in the Solve menu, we select where we want the analysis to solve, locally or in the cloud. Once the analysis is finished, we have the results ready to be inspected and interpreted. We can see that the temperature on the fins is pretty high and could be dangerous to a person that touches them. So we could decide to increase the size of our fins. At the end of the day, there is a cost associated to the extra material, But right now, finding out and understanding if we are underdesigned or overdesigned is incredibly valuable. Creating a new simulation model and rerunning the analysis with the same settings allows us to use the compare workspace to look at results from both models at the same time. We can see that the larger fins reduces the temperature in the areas that people are most likely to touch. I hope this helps. Happy simulating!